Hey everybody, my name's Kevin. Big thanks to Fonzie and crew for having me. I'm pumped to be here. I've been to a few of the events before and they never miss, and the beer and pizza don't hurt either. All right, so we're here to talk about when Jira tickets can fix themselves. First though, a little bit about me. I'm Kevin, head of engineering at Spot and Tango, leading a 10-person engineering team, but the company's doing over 100 million ARR, so we're punching a little above our weight class and we need more velocity. Spot and Tango is a premium pet food. Just hold it really close to the mouth. Okay. Spot and Tango is a premium pet food subscription brand. We make pet food tailored to your pet's needs. Previously, I worked at a company called Courier Health, Amazon, and Cisco. So the agenda for the talk is going to be a little bit about Spot and Tango and their business that will help give you context as to what we're building with AI and SDLC bottlenecks, and then the solution that our in-house engineering team is using, Fetch AI, and a little bit about what's next with that tool that we built. So, Spot and Tango manufactures dog food. We have a plant in Allentown, and the main goal of our company is to drive customers to our website so we could get them this awesome dog food. So we're advertising on all different platforms, TikTok, Instagram, things like that, and the goal is to get customers to our marketing site. From there, they learn a little bit more about what we do, and if they like what we're doing, they'll move on to our funnel. We ask customers questions about themselves and their pets, and then we tailor a pet plan just for them. Some of the things that go into this algorithm are pet size, pet weight, lifestyle, activity, breed, things like that. So we don't use AI for this algorithm because we want the output to be deterministic. The output is calories per day. So if we have two pets with the same exact characteristics, the calories per day should be exactly the same. Most of the AI tooling that we're using is for developer productivity or other employee enhancements to improve their outputs. So once a customer subscribes to our software in the funnel, then they manage their subscription in the customer portal. And that's pretty self-explanatory. As you can imagine, they could add more snacks or supplements, or if you have a puppy, you can increase their weight because that's a really big thing with dogs. As they're growing, they need more calories. And then we have this internal tool that we call BARK. You'll learn that we love acronyms at Spot and Tango. BARK stands for Business Administration and Record Keeping, and that's really just a dumping ground for all of our internal software, whether that be like discount management, creating replacement orders if a customer loses their box, running promotions, and now a new tool that we have called Fetch AI. So I want to talk about a familiar pattern that most software developers probably faced before. In D2C, direct-to-consumer businesses, marketing teams ask us for a lot of things on the fly. So in this case, for Black Friday, Cyber Monday, the marketing team wants to test new hero images and copy placement. Product team says, sure, let's talk more about that. I'll make a ticket and partner with engineering. But then the engineering team says, yeah, would love to do that. Assuming we can make it out of this sprint, I'll get to it next week or in 2 weeks, however long your sprint is. So clearly we have a bottleneck here. The tool that we built, Fetch, is not meant to do projects like launching your business in a new marketplace, like in Canada, or launching a product like PayPal, doing an integration like that. It's for these small tickets that really have to wait, and then you don't get to test things like this and learn if this festive copy would have driven more conversions. So the idea here is, how can we fast track requests like this to get quick business wins so that the 10 engineers on my team could do the really big important stuff while still doing the needs of the marketing team when they have a last minute request like this. So then that leads me to show you where are we getting these efficiency gains and how does it happen. So Fetch is this internal tool that we built using Cursor. So it's completely wrapped around Cursor, and the automation happens in the engineer writing the code and the engineer drafting the PR manually. So the time savings can be anywhere between an hour to 6 hours. It really depends on how simple the ticket is. Obviously, 6-hour development savings isn't going to be on like a hero image. That's going to be really quick. Maybe you save an hour on that. So one of the reasons we chose Cursor is because it's compatible with all of the major LLMs. And another huge reason for this is in this scenario I gave you before, a product engineer could literally just put that input into Fetch and then get an output. Now the bottleneck moves from the engineering person's bandwidth into code review. So now if we can get someone to code review this and QA it, we've pushed the bottleneck down a little bit further into the process. And obviously this allows engineers to work on higher impact work. So without further ado, here is a little screenshot of the tool that we built. For context, we built this in a matter of 2 weeks just to get an MVP out. It came out in September 26th, and my team's been using it since. So in the top left corner, you have a Jira ticket. On the right side, you have a GitHub repository that you select. And once you select that GitHub repository, there are all sorts of repo rules for that repository, like linting rules, styling commands, GitHub templates. So when you put up a PR, we have templates. And that is all the automation that we're getting from using something like Fetch. So we give it these ACs, and then we hit generate pull request. That sends a request to our backend, and then our backend has all of that data about these specific repo rules that we've built in, and then it makes a call to Cursor. So the only thing that we're using Cursor for here is to spin up a new agent, and then to get the status back from that agent. Once you hit generate pull request, the product person or the engineer just can see when Cursor is done generating the code, and then the output is on the right, the pull request that we've opened. And Fetch is sitting in our GitHub account, just like all of our other engineers, so it's very metric and measurable how many PRs Fetch is doing for us. And on the left side, we have the Cursor output. This is, honestly, it's another choice. We could have just gone with this, but there are some reasons to not just use the Cursor agent. We could have bypassed the whole thing. Some of the downsides of just using the Cursor tooling would be the backend governance, like I was mentioning. We have all of the request proxy for our backend, so you would have to add all of these roles, like acceptance criteria, steps. You have to add that to every request in Cursor, but our backend just already has that. Another is Bark is just more approachable than this Cursor UI, and the metrics that I've already mentioned. And I think the adoption psychology here is that I think the team is using Fetch more than they would be using this Cursor agent screen that you have on the left directly from Cursor. So yeah, just talking really fast about what's next is in the future, we would like to create some, take an Jira epic, like the product team writes a full PRD, engineers create epics with stories, just to make sure we're not missing any acceptance criteria. That's a potential future idea for Fetch. And a third one is to generate and maintain integration tests. Thanks, that's the talk. And if you'd like to connect with me, feel free, happy to connect and give out any Spot and Tango discount codes for your dog or yourself.
Hi everybody, I'm Daniel Habib. I'm the founder of True3D Labs, and today I will be talking to you about how we use AI to lift standard videos into 3D. So before we jump in, a little bit about myself. True3D is a graphics research lab building the next evolution of visual media. And we build AI models and infrastructure that lets you engage with, create, and stream 3D videos in real time. Before this, I was a software engineer at Meta, working on live video infrastructure. I worked on the code that's set under Facebook Live, Instagram Live, and VR Live Video, billions of users on that stuff. Before that, I worked at Refinery29, working on video tools. And then before that, I was unemployed, teaching myself how to code. So if you have questions about that, you're in that situation, come talk to me after. I've got plenty of tips. Today, we're going to be talking about what 3D video actually means to us, how 3D media is created today, and how neural networks are transforming 3D creation. So when I say 3D video, a lot of people think about 3D movies. And that's actually not what we're talking about. I've seen Spy Kids 3D, I've seen Avatar in 3D, and here's a quick question for everybody. What year do you think was the first 3D movie where people went to the movie theater and put on glasses? Does anyone have a guess? Okay, you guys are all very close. It's actually 1922. And it was a silent film. This was 5 years before the advent of synchronized audio, okay? So, kind of crazy. What actually does 3D mean in this context? For movies, this is a parallax effect. It's a simple left and right eye that gives you some sense of depth. Like a fist punching towards you, you might feel like, whoa, right? The whole movie's built around that effect. That's not what we're talking about, okay? We're not talking about this. We are talking about fully volumetric video. We describe the front, the back, the left, the right, every part of this. It does not matter what angle you look at this content from. We have a bunch of demos. Come talk to me after, or even you can try that link and see one of them. But we are talking about volumetric video. The way you capture this content today is you go into a giant dome with like 300 cameras, okay? It's kind of insane. There's only dozens of those in the world, and it can cost thousands of dollars for 30 minutes to even capture one of these. But I want to talk about 3D first, what 3D video actually is comprised of. So to talk about 3D video, we need to quickly talk about 2D video. Now, a video you could think of as a series of images that happen in rapid succession that create the illusion of motion. Those images are created by what most of you probably know as a pixel, right? You could think of it as a little square. It's not technically that, but you could think of it that way. And each one just describes color. Simple RGB, 3 bytes, nothing crazy. In the 3D space, we can't actually control exactly where the user is going to be looking at this content from. People like to get really close to this stuff or back out all the way. So we need it to look awesome at all of these different positions. And this actually requires a new primitive. Pixels don't look that great when you get that close. And this is where Gaussians come in. Okay, Gaussian splats, you've probably heard of, voxel splats, terms like that. The problem with Gaussians is they are way more complicated. They require significantly more data per primitive, okay? You need millions of these things. You could think of them as, instead of a square, an ellipsoid with opacity, and they stretch, and they can look different from different angles, and basically they're more complex, okay? So the other tidbit about Gaussians is you have to train them. This isn't theirs. You can't just say, oh, this part's red, so this is a red pixel. You actually need them to learn their position. And this process is very complicated, takes a lot of time, but what I'm showing you here in the top right is the ground truth, that's the target, and what you're watching are Gaussians actually learning where they belong. And in practice, this is what it looks like on an actual splat, like a Gaussian splat that you would create. That's me. Now, the problem here, like I mentioned, it takes a lot of cameras to do this. No one has the capacity to do this practically. So what do? What's the solve? Well, if you are a broke startup, you create a rig like this. You go to Home Depot, you get PVC pipe and PEX tubing, a lot of duct tape, some foam tubing to hold the phones, and then, fun fact, you can actually buy and return iPhones in bulk every 14 days. So there are a lot of Apple stores in the city, and they get mad at you, and you can't go back to the same one because they don't like me, but you can do this. So we did this. But actually, the answer for solving this are diffusion models. Now, you can actually use video diffusion models to generate all of those additional views. And what do I mean by additional views? We record video on our cell phone. This is how most people do it, right? I'm not walking around with a giant dome with 300 cameras. But as video diffusion models get better and better, we can generate those views based off of your single input. So a great paper that covers this topic is Diffhuman 4D. I highly recommend you guys all check it out. And this is the solve moving into the future. Now, in practice, what does this look like, generating all these views? You need that first single view to do this multi-view video diffusion. And you need to give something that's called camera extrinsics. It's a fancy word for position and rotation. You basically have to tell the video diffusion model, relative to where you are, where should I generate a new view, right? Not that crazy, but you have to do this like 300 times. And it's slow. It's very, very, very slow because video diffusion models are very slow, and you need many of these views to create these 3D reconstructions. So it's 50% is actually extremely generous. It's more like 80 to 90% of the processing time. But actually creating the splats themselves is a really slow part. The cool thing here is that diffusion models are getting cheaper. They're getting faster. You see examples of real-time diffusion models now, and very soon you'll be able to run these on your server. So the trend here is that the diffusion part of this process is going to get cheaper and cheaper. The other thing about this is it's extremely memory intensive today. You're not pulling this off on your MacBook. Like, you need at least an A100, probably an H100 or 200, especially for longer videos. And where this is headed though is pretty clear, that as the diffusion models get cheaper, faster to run, you'll be able to just take a single video and it will turn into 3D. And this will be the standard way we think that people engage with media. That's it.
Hi everyone, my name is Akarsha, and I'm a part of Bedrock Agent Core Memory team. But here, I'm not going to talk about this. I'm going to take a step back, and since most of us here are working in AI, and I'm guessing a lot in Agentic AI, I want to take this opportunity and talk about context engineering. Because having talked to so many customers, I've realized that as soon as customers hit a point where they are like, oh, my agent is not performing well, they move so fast to fine-tuning, the model distillation, and all of the other complex ways of working or creating an agent. But one fundamental thing a lot of people miss out on is the context engineering. A lot of power lies in this. So first of all, talking about us in the last, since we have been building agents, we are talking so much about technical capabilities, right? We have achieved remarkable technology in terms of how we are adding capabilities in the agents. We are adding more and more tools, we are adding APIs, we are creating more and more protocols, orchestration, complex orchestration or workflows. But at the end of the day, when we want our users to use these agents, we need to have good experience. And fundamentally, agents are stateless. So they don't really have anything more than what you're providing in that token window. And that's what I want to highlight today of how to create stateful, context-aware agents, right? And the point is that why do we need to care so much about it? Because when agentic systems mess up, right, most of the time that's because of the LLM. And now it could be one of the two options. Either the model itself is bad, right? And let's face it, today with the improvements of the models, we have pretty good models, they don't hallucinate that easily. And therefore, let's say the blame goes to the second option, right? Which is the context. So what we're providing in that LLM, right? To that LLM, what we are sending it. And that's where context engineering comes in. So one way, easy way to do it is that you provide everything in there. You have whatever documentation you have, whatever memory you have, just provide everything. But the context rot concept is real. So what it does is, it has the transformer models, how they're trained. They're firstly trained on smaller context windows, right? So that's where they're good. And they are trying to find out the pairwise similarities, so pairwise relationships between all the tokens that it has access to. And that, the longer the context window, the more complex it gets, and the worse the output gets. So therefore we have issues like hallucinations. So if you are providing too much information, it might not even consider what it has been trained on, because it gives too much priority on what the context is, right? And that's what causes hallucinations. Then we could have context overload. There's so much information that we're providing it that it just forgets what original task it was there to solve. Or it could have context clash. So within that 10 million token window. Today we can provide 10 million token window, which is crazy. But within that token window, we can provide all of the information which might be confusing or might be, slightly contradicting. And that's where it could have the reasoning errors. So just like humans, communication is important, and how you're formatting that information that you're providing it becomes significantly important. So here, what is context engineering? Very briefly, it's the process of designing and optimizing instructions. So essentially, how you are designing what you're providing to the model, right? So context overall includes system prompt, user prompt, profile information, identity context, tools, memory, and probably the user information that you're providing. And how we are curating that context window is what is of, let's say, the most relevance here, right? So we have to define as smaller a context window as possible, such that we are able to get equally good results. And now I work for agent core memory, and therefore I only have the benchmarks for that. So just changing out of that, let's say, out of that entire thing that you could actually refine. So you could refine the documents, the tool prompts. You could only provide the relevant tools. You could only provide, let's say, the relevant message history. So out of all of those things you can actually optimize on. I have only optimized on the memory here, and roundabout achieved same correctness scores with 70 to 90% of compression rates. And this is amazing. So we are providing 65? I can't see it. 68. So 68 to 95% compression rate. Even with that, we have more or less exact amount of correctness. So now talking about why how can we actually do this in real. So whatever I mentioned was just for memory, but think about it. If you do it for all different aspects, you refine the tools that you're providing in, you refine the RAG that you're providing in. Doing all of those things, you can actually improve the quality of the output quite a lot. So discussing some strategies here for practical scenarios. So first of all, we're talking about the writing context. So here we talk about saving the information outside of the context window. So think about it as note-taking, how we do it, right? So important information, just write it down somewhere and retrieve it later when you need it. And here we can think of techniques like Scratchpad, memory. You can just create a notes file and then retrieve it back. It's very popularly used in the Cloud Code or these coding applications. The second one is around selecting context. So this essentially means only select the relevant information that you need in the context window, right? Third one is about compressing the context. So here we are aiming to manage the token blast. So essentially trying to reduce the context size, right? We can summarize the previous conversation, we can prune, as in only keep the last n messages plus the summary or so. So we can prune and to avoid having too many tokens. Then the last one is the isolating the context. So this essentially talks about how you can define, let's say, one goal for a single agent and only provide it the information that it needs to solve or to achieve that goal. And divide and conquer kind of a technology. So here we talk about having multiple agents that do their own task, and then at the end of the day, coming together to solve a bigger problem, right? So this we have seen a lot with research agents lately. So as deep research agents are coming out, we have multiple swarms of agents or a workflow that basically works together to come to a final research output. right? Now I think I will pause here, and I will not go into what different features we have at Amazon. So there are a lot of features that can help you solve these things, but I just wanted to take this time to explain the importance of context engineering, and hoping that as AI engineers, you go back to your companies and give it some priority, because I don't want to have any other directly fine-tuning conversations. So, yeah. Thank you.